Hi, welcome to Digital Electronics. Today I'm going to talk about the next chapter under chapter 2, Signed and Unsigned Numbers. So this is the outline of the chapter 2 and I'm going to focus on the subchapter Signed and Unsigned Numbers with Arithmetic Operation. In the last previous class, I have mentioned about binary subtraction issues. So when you have a normal decimal subtraction, this is the maths 4 minus 3 is equal to 1. But you are doing it under the binary subtraction in theory part. So 4 is 0, 1, 0, 0 and 3 is 0, 0, 1, 1. When you minus this, you're going to have 0, 0, 0, 1, which is correct with the mathematical. But what will happen when you have a small number minus or add 3, which is bigger number? So minus 4, which is supposed to be minus 0, 1, 0, 0, and you're going to have a plus 3, which is plus 0011, and when you do the arithmetic you got something like this, and also you also have a negative sign in front. So to represent this negative symbol, because it is not possible because in digital only 0 and 1 is exist. So how you going, and also it is not matched with the math solution. So this is the issue over here. So how are we going to solve this? So this is very important, and we need to, before we do this, we need to understand the mathematical issue. So in whole number, it consists of negative infinity to positive infinity. So you have a negative infinity over here. It started with negative 1, negative 2, negative 3, so on. And you have a 0 over here. You have positive 1, positive 3, and until positive infinity. So in the digital representative of this positive number, which is we call unsigned numbers, so it's not it's very easy. So therefore the decimal 0, 1, 2, 3 going to have a binary numbers, and these binary numbers can be used to represent 0 and any positive range of whole number. So this is okay. So how about in the negative number? Let's say you have a negative 1, which is negative decimal, negative 1. And in your positive side, you should have 1 is equal to 0, 0, 0, 1. But in this negative, how are you going to represent this? Are you going to do show it as negative 0, 0, 0, 1? Are you going to have 0, 0, 0, 1 and you have a bar over there? Or maybe you're going to have in reverse, you put 0001, the MSB on the right side and LSB in the left side, which is very weird, you know. So none of these representative are suitable. So therefore we need a new or a universal method to show this negative 1. So let's say you have a negative 1 decimal, and 1 is equal to 0001 or maybe 001. This is in a 3-bit binary numbers, and we have a header. This header is we call MSB, which is most significant bits, which is the fourth bit. And for positive, we can sign it as 0, and to have a negative side, we're going to sign it as 1. So for example, negative 1. So you're going to have the normal 001, and then the header is 1. So you're going to have a 1 in front of it. At the final is going to have 1001. This representative must match with the need of simplified arithmetic and universal usage. So as mentioned inside. So in signed numbers, have we solved this problem? So just by adding 0 or 1 in front of a binary number, is it considered as so? Let's test. In a normal mathematical, 4 plus 3 is equal to 7. So the binary numbers 01100 plus 0011 is equal to 01111. So this is equivalent to 7. So this is good. So how about subtraction. 4 minus 3. 4 is 0, 1, 0, 0. And how about 3? So we just put a 1 in front and make it positive. And then we try to add it up. 0 plus 1, 1. 0 plus 1, 1. 1 plus 0 is 1. And 0 plus 1 is 1. Is it equal to 1? No. So how are we going to solve this? Let's say we put it as a 0 in front, because we say is changed to positive, because we're going to change from negative to positive. We're going to add it up. We're going to minus it out. So 0 minus 1, we borrow from outside, and then we get 1. And also same cost, 0 minus 1 is we already borrowed, and we're going to have 0. And this is 0. 0 minus 0 is 0, and 0 minus, so this is correct. Is equal to this one. How about this one? So minus 4 plus 3 is supposed to be have negative 1. How about this one? 1, 1, 0, 0. We already changed the minus to become 1. And then we're going to plus it, but it's not happening over here. But how about negative? Let's say we change the arithmetic to negative. So this is already in a sign number 1100, and this is 0011, and we're going to minus it, and we got 0111, which is also not correct. So we have to have a simple representative, at the same time doesn't create any problem in arithmetic. So this is how we're going to do. So let's say we have a minus 13 in decimal. In a sign magnitude, which is we're going to have only negative 13. So in positive 13 is supposed to be 1101 to the base of 2. So how to change to a sign magnitude? So just bring your 1101 to here, but this is not the final answer yet, so that's why I put a big X over here. We're going to add on 1 in front of it to show it is a sign number. And then we're going to, because it's very weird to have only 5 bits, so we're going to put it, usually we show it in 4 or 8 bits in one particular final answer. So that's why we're going to have a final result negative 13 in form of sign magnitude. You're going to have 0001 1101. How about first complement in form of first complement? So like previously, positive 13 is going to have a 1101 in form of we're going to go do the first complement. So you're going to have we just bring the exactly 1101 to here, and then we're going to invert everything. 1101, it becomes 0010, and then in form of 8 bit is going to represent as 00000010. This final answer is only for first complement representative. How about second complement? Negative 13 is equal to 1101 as earlier. We're going to do the first invert from 1101 become 0010, and then we're going to add 1 because this is a second complement, so we're going to add 1. So this is my bad. And then we're going to add 1 and become 0011, and in form of 8 bit you're going to be 00000011. So you can have a representative of 3 different representative for sign number of negative 13, here, here, and here. Let's try to use the second complement to solve the arithmetic problem. So this one we already discussed earlier, so this is okay. So how about 4 minus 3? So 4 is equal to 0100, and you're going to minus 3. So this one is changed to 1 1. Okay, when we have this one 3 is 0 0 1 1, and then we do the complement. You're going to have 1 1 0 1, and then you add up, you're going to have this one, and then you have a carry outside, add another one, become 0 0 0 1. How about subtract? Negative 4, it become 1 1 0 0, and then you're going to add up 3 0 0 1 1. Total of this become 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1. So you're going to have 1 1 1 1. Is it same with this one? Not yet, because this is in second complement. You need to change back to get 0 1. So this is the explanation for this one. And then so like I said, negative 4 is equals to 1 1 0 0, and this one is 1 1 1, and then we do the second complement. We're going to have 0 0 0 1, which is negative 1, and for this part also is already explained as before. So finally, we are able to represent the negative binary in form of signed number, and also able to solve arithmetic without any problem. So self-task, you have two questions over here. You have negative 13, 35, negative 35 to change to binary. So please complete this one. And also the second question. This is a little bit challenging, but it's possible. So this is the answer. So another part I need to emphasize is we have an initial value. Let's say we have an initial value of 1 1 0 0 0 0 1 0, and then we do the first complement. We got 0 0 1 1 1 1 0 1, and second complement you add up 1, and final answer is 1 1 0 0 0 0 1 0. If you watch clearly, it have similar answer. The final value is similar to the initial value. This is not error. It's because this is possible for second complement to exist at the same time or similar to the initial value. So please take note of it. So same goes to this example and also this example. So the range of binary numbers. So for unsigned binary numbers, the range is from 0 to 2 to the power of n minus 1. So for example, for 8-bit, from 0 to 2 to the power of 8 is 256, minus 1, you're going to have answer 255. So for 8-bit binary, for unsigned number, it will be from 0 to 255. And for signed number is 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. So for 8-bit binary, you just put 8 over here, 8 minus 1, 2 to the power of 7 is 1 to 8. So you're going to have a negative over here. Yeah, my mistake over here. And then later on, for similar to this one, 2 to the power of 7 minus 1 is going to be plus 2 7, sorry, 1 to 7. So minus 1 to 8 to plus 1 to 7 is the range for signed number for 8 bits. So make sure your system design able to handle all the bits, because you're going to have a overflow, and sometimes overflow can make a situation become a little different than what we expected. And this is very important to make sure you understand over here. For example, this one, they have an overflow, so but overall at the end of this answer is correct, right? So yeah, and that's all for this particular talk. And next you can directly to the document 2.3, and we're going to talk about hexadecimal. Thank you.